Hello, welcome back to Sleep Science. Wherever you are right now, whatever the room sounds like, whatever time it is, this is a good place to be. Get comfortable, let your weight settle into whatever you're lying on, let your shoulders drop a little. There's nothing you need to do tonight except listen, and even that is optional. Tonight we are going to talk about a planet that should be completely dead. A planet hotter than an oven, covered in acid clouds, crushed under an atmosphere 90 times heavier than ours. And yet, something may be alive there, not buried under the surface, the way we sometimes imagine life might hide on Mars. Not in some deep subsurface ocean protected by kilometers of ice, but floating, right now, in the middle layer of the Venusian sky, in clouds made of sulfuric acid at temperatures a human being could theoretically survive, drifting through an atmosphere that sits between the brutal cold of space and the crushing, melting violence of the surface below. That's the strange thing about Venus. It has a habitable zone, a narrow ribbon of altitude where the temperature drops to something almost reasonable, where the pressure feels something like home, where, if you squint at the conditions through the lens of everything we know about life on Earth, you might just be able to imagine something small and quiet and persistent making a go of it. And in September 2020, a team of scientists found something in those clouds that didn't belong there. A gas called phosphine. A gas that on Earth is made by two things and two things only: industrial processes and living organisms. There are no factories on Venus, which left one explanation, one that nobody in the scientific community was quite ready to sit down and look at calmly, because it was the explanation that changed everything, or might change everything, or might eventually be explained away by some chemistry we don't yet understand. We don't know yet. That's the honest answer. We don't know. And that not knowing is one of the most interesting places in all of contemporary science. A genuine open question, not a thought experiment, not a philosophical puzzle. A real, unresolved, peer-reviewed, telescope-confirmed puzzle sitting in the clouds of the planet next door. Tonight we're going to walk through it slowly. The planet, the discovery, the controversy, the alternatives, the implications, all of it. At the pace it deserves, not rushing toward a conclusion because there isn't a clean conclusion yet, just moving through the facts and the strangeness and the quite extraordinary possibility that we are not alone in the solar system. You don't need to stay awake for any of this. Let it come to you. Let the ideas wash over you gently. If you fall asleep somewhere in the middle, you will wake up tomorrow having been, however briefly, in the presence of one of the most interesting open questions in human history. That seems like a good way to spend a night. So, let's begin. Venus is the second planet from the Sun. You can see it sometimes just after sunset or just before sunrise, brighter than anything else in the sky except the Moon. It's been called the evening star for as long as human beings have been looking up. Ancient astronomers loved it. They wrote about it in ways that suggest a kind of reverence. Something that beautiful and that bright, hanging in the twilight sky, seemed to demand a story. The story they eventually discovered was not what anyone expected, because Venus up close is one of the most hostile environments in the known solar system. That brightness, the thing that made it so beautiful from a distance, is sunlight reflecting off an unbroken blanket of thick white clouds that cover the entire planet. Those clouds look almost gentle from Earth, soft, like something a Renaissance painter might have imagined as the atmosphere of a paradise. What's inside them is the opposite of paradise. Let's start with the surface, because the surface of Venus is where the story of hostility really begins. The average temperature at the surface of Venus is around 465 degrees Celsius. That number takes a moment to become real. On Earth, water boils at 100 degrees. Steel melts somewhere above 1,300 degrees. Lead melts at around 327 degrees, which means the surface of Venus is hot enough to melt lead. Not just hot enough in theory, routinely, continuously, hot enough to melt lead. At night, during the day, at the poles, at the equator. The temperature at the surface of Venus barely varies at all because the atmosphere is so thick and so dense and so effective at trapping heat that the whole planet has essentially reached a kind of thermal equilibrium. A steady, relentless, planet-wide oven. The Soviet space program in the 1970s and 1980s sent a series of probes to Venus. They were called the Venera probes, and they are among the most remarkable engineering achievements in the history of space exploration, for reasons that have nothing to do with their success and everything to do with how quickly they failed. The Venera probes were built to be as tough as the engineers of the Soviet space program could make them. They were designed to survive the descent through the Venusian atmosphere and to function briefly on the surface. The longest any of them lasted was just over 2 hours. Venera 13 in 1982. 2 hours and 7 minutes, after which the heat and the pressure simply overwhelmed everything. The electronics failed. The seals failed. The instruments, one by one, went quiet. 2 hours was considered a triumph. Think about that for a moment. The engineers who built those probes knew they were sending them to their deaths. They built them anyway, as well as they possibly could, and felt a kind of pride when their machines survived long enough to send back a few dozen minutes of data before the planet consumed them. The cameras on Venera 13 captured images of the surface. Flat, angular rocks, a strange orange-yellow light, because the thick atmosphere filters the sunlight down to something that looks like the inside of a very old, very warm room. Nothing moving, nothing growing, just rock and light and heat. Those images are still the clearest pictures we have of the Venusian surface. 40 years later. Nobody has been back, not to the surface, because there is no easy way to build something that survives there long enough to justify the effort. The planet defeats every machine we send. But it's not just the heat. The atmospheric pressure at the surface of Venus is approximately 92 times the atmospheric pressure at the surface of Earth. 92 times. The pressure at the bottom of the deepest part of Earth's oceans, the Challenger Deep in the Mariana Trench, is about 1,000 times atmospheric pressure at the surface. So Venus's surface pressure isn't as extreme as that, but it's the kind of pressure you would encounter if you went about 900 meters underwater here on Earth. Enough to crush most things designed for surface conditions. Enough that the air itself at the surface has a density not far from the density of liquid. You wouldn't be breathing it so much as struggling against it. The air at the Venusian surface is almost thick enough to swim in. And that air is mostly carbon dioxide. Not the trace amounts of carbon dioxide we're dealing with in Earth's changing climate. Not the small percentages that plants use for photosynthesis. Pure, dense, choking carbon dioxide making up about 96% of the entire atmosphere. The rest is mostly nitrogen, with traces of sulfur dioxide and other gases. No free oxygen, no water vapor to speak of, not at the surface. Nothing that any life as we understand it could breathe or drink or use. The clouds that cover the planet so completely and so beautifully from a distance are made of sulfuric acid. Droplets of concentrated sulfuric acid forming in the upper atmosphere and cycling through a complex weather system that has been going on for longer than any human civilization has existed. The acid rain that falls from those clouds never reaches the surface. It evaporates long before it gets there because the lower atmosphere is so hot that even acid doesn't last long falling through it. But in the cloud layer itself, the acid is real and persistent and dense. sulfuric acid at concentrations of up to 90%. On Earth, concentrated sulfuric acid is one of the most destructive substances used in industrial processes. It dissolves metals. It destroys organic tissue almost instantly. It reacts violently with water. We keep it in specially designed containers and treat it with enormous caution. On Venus, it's just the clouds, just the sky. 60% of the visible disk of the planet, when you look at it through a telescope, is clouds made of something that would destroy most materials almost instantly. And yet, here is the thing. Here is the strange, counterintuitive thing that sits at the heart of everything we are going to talk about tonight. Life on Earth has a habit of showing up in places exactly like this. Not exactly like the Venusian surface, which really does seem to be beyond what any known biochemistry could tolerate, but in conditions that, by any reasonable measure, should be lifeless. In boiling acid pools, in the cores of nuclear reactors, in the permanent deep cold of Antarctic ice, in the crushing darkness at the bottom of the ocean, in clouds, in the sky, life finds ways. That phrase has been repeated so many times that it has become a cliché. But clichés are usually clichés because they started out as something true and got repeated until the truth was worn smooth. Life does find ways. Life on Earth has been finding ways for roughly 4 billion years, and in that time it has colonized almost every corner of this planet, including corners that look, to us, completely uninhabitable. The question of Venus is not really whether life could exist anywhere on that planet. Most people who study it seriously agree that the surface is almost certainly too hostile. The question is that narrow ribbon of sky, that specific band of altitude floating above the worst of it, where the conditions are, by the standards of the solar system, almost gentle. And in that almost gentle layer of sky, in the year 2020, a team of scientists found something that has been quietly reshaping the conversation about life in the solar system ever since. Let's get to that. But first, let's understand how Venus got to be the way it is. Because that story is, in its own way, just as extraordinary as the phosphine discovery. Just as strange. Just as worth sitting with. A planet almost identical to Earth, in the same solar system, born from the same cloud of gas and dust at roughly the same time. And it ended up like this. Which raises a question that Earth scientists think about more than they used to. It raises the question of how close we came to being Venus. Somewhere around 4.5 billion years ago, the solar system was a disk of gas and dust and rock swirling around a young star. Out of that disk, planets formed. They formed through a process called accretion, which is a word that sounds more complicated than it is. Accretion is just accumulation. Small particles colliding, sticking together, forming slightly larger particles, which then collide with other slightly larger particles, and so on, over millions of years, until you have something the size of a planet. It's a slow, violent, beautiful process, and it happened more or less simultaneously across the inner solar system. Venus formed at a distance of about 108 million kilometers from the Sun. Earth formed at about 150 million kilometers. By cosmic standards, those distances are not very different. The two planets are neighbors. They were born from similar material, at similar times, under similar conditions. And for a while, in the early solar system, they may have been surprisingly similar worlds. Both planets are roughly the same size. Venus has a diameter of about 12,104 kilometers. Earth's diameter is about 12,742 kilometers. They are, in planetary terms, nearly twins. Venus is about 82% the mass of Earth. Its gravity at the surface is about 90% of Earth's gravity. If you stood on Venus, you would weigh slightly less than you do on Earth. The difference would be noticeable, but not dramatic. Both planets probably had liquid water early in their histories. Both planets had thick atmospheres. Both planets were likely warmer than they are now because the early sun was slightly dimmer and the planets were geologically active and busy producing heat from their own interiors. Both planets, in other words, had the raw ingredients for what we might loosely call habitability. And then something happened to Venus. The word something is doing a lot of work there, and scientists are still debating exactly what that something was and when it happened. But the broad outline is understood. Venus underwent a runaway greenhouse effect. A greenhouse effect is, at its core, a simple phenomenon. Certain gases in a planet's atmosphere are transparent to incoming sunlight but absorb outgoing infrared radiation, the heat that the planet radiates back into space. This traps energy in the system. The planet warms. This is not inherently bad. Without the greenhouse effect, Earth's average surface temperature would be something like -18 degrees Celsius. The natural greenhouse effect on Earth keeps the planet warm enough for liquid water and life. It is, in that sense, one of the reasons we exist. But greenhouse effects can go wrong. On Earth, the climate system has various feedback mechanisms that tend, over geological time, to regulate the temperature. When carbon dioxide levels rise, for instance, the increased weathering of rocks tends, over millions of years, to pull that carbon dioxide back out of the atmosphere. The carbon silicate cycle. A slow geological thermostat that has kept Earth's climate within a range compatible with life for most of its history. Venus either never had those feedback mechanisms in the same way, or it had them and then lost them, or it simply crossed a threshold beyond which they could no longer operate. And once the runaway began, there was no stopping it. Here's how a runaway greenhouse effect works, in the simplest possible terms. The planet starts warming. As it warms, water evaporates more readily. Water vapor is itself a greenhouse gas. More water vapor in the atmosphere means more warming. More warming means more evaporation. More evaporation means more water vapor. And so on. A feedback loop that feeds itself, accelerating, with no natural break. On Venus, this process may have run to completion. The oceans, if Venus had them, evaporated entirely. The water vapor rose into the upper atmosphere, where ultraviolet radiation from the sun broke it apart into hydrogen and oxygen. The hydrogen, being light, escaped into space. The oxygen either escaped as well or was absorbed into the rocks. Either way, it didn't stay as water. Over millions of years, Venus lost its water almost entirely, and without liquid water, the geological processes that might have regulated the carbon dioxide cycle either stopped or never started. Carbon dioxide, which on Earth is cycled between the atmosphere and the rocks through weathering and volcanism, built up in the Venusian atmosphere instead of cycling back into the planet. It piled up, layer upon layer, an atmosphere that became denser and denser and more effective at trapping heat. The surface temperature climbed, and climbed, and climbed, until it reached what it is today. 465 degrees Celsius on average, the hottest surface in the solar system, hotter even than Mercury, which is much closer to the Sun but has almost no atmosphere to trap heat. Mercury gets hot during the day and then loses that heat rapidly at night. Venus just stays hot, all the time, everywhere. The whole planet is wrapped in its own misery, sealed inside an atmosphere that lets the sunlight in and never lets the heat out. There is something almost philosophical about that. A world that absorbed too much of what came to it, held on too tightly, and ended up burning itself from the inside. A cautionary tale written in planetary physics. But here's where it gets interesting in a different way. Because scientists think this transformation of Venus from a potentially habitable world to the hellscape it is today may not have happened all at once. It may have been gradual. The early Venus, before the runaway greenhouse really got going, may have looked quite different. Some climate models suggest that Venus could have had liquid water on its surface for as long as 2 billion years. 2 billion years. That is an enormous amount of time. On Earth, complex multicellular life didn't really get started until about 600 million years ago. Life itself has existed on Earth for maybe 3.5 to 4 billion years, but for the first several billion years, it was mostly microbial. Simple, small, persistent. And in 2 billion years of potentially habitable conditions, early Venus might have developed its own version of that. We have no way to know. The Venusian surface has been resurfaced, geologically, by massive volcanic activity, possibly as recently as 500 million years ago, maybe more recently than that. Whatever geological record early Venus might have had is likely buried or destroyed. We cannot go to Venus and find ancient fossils the way we might hope to find them on Mars, preserved in sedimentary rock. But here's the thing about life. Here's the thing that connects the ancient possibly habitable Venus to the modern possibly life-bearing clouds. Once life gets started, it tends to be very hard to stop completely. It adapts, it migrates, it finds niches in places that weren't niches before. If life existed on the surface of early Venus, and if the runaway greenhouse process was slow enough, at least some of that life had time to adapt. Time to move upward into the atmosphere as the surface became increasingly hostile. Time to find that narrow band of relatively gentle sky and make it home. This is not a mainstream hypothesis. Most scientists would say it's speculative at best. The conditions for such a migration, the timing, the biology, the chemistry, are all deeply uncertain. But it is not impossible. And the universe, as we keep discovering, has a complicated relationship with impossibility. There is a version of this story in which life on Venus began billions of years ago, when the planet was still gentle and has been slowly, quietly, stubbornly surviving in the clouds ever since. Adapting generation by generation to increasingly harsh conditions. Growing smaller, perhaps. Growing stranger. Living in droplets of acid the way bacteria on Earth live in droplets of water. Never knowing, in any meaningful sense, that the world below them had become something unlivable, just floating, persisting, doing what life does. The Venusian atmosphere takes about 4 Earth days to circulate all the way around the planet. The cloud particles drift with that circulation endlessly. A microbe drifting in the Venusian clouds has circumnavigated the entire planet thousands of times over the course of a year. It has seen every part of the sky above a world it can never touch. It has drifted through the acid and the heat and the pressure, and it has continued, quietly, to be alive. Maybe. We are, at this point, firmly in the territory of maybe, of possibly, of the kind of careful, evidence-conscious speculation that good science permits and bad science ignores. The point is not to say that life is there. The point is to say that the conditions in that cloud layer are not obviously incompatible with life in the way the surface is. But we weren't really thinking about this seriously until September 2020. We were mostly thinking about Mars. Mars got all the attention. Mars got the rovers and the landers and the orbiters and the press coverage and the popular imagination. Mars is cold and dry and thin atmosphered, but it had water once, and it has ice now, and it has a surface you can stand on and examine in something like reasonable conditions, at least if you have a spacesuit. Mars feels tractable. Venus feels like a nightmare. And so we kept looking at Mars, and we kept finding tantalizing but ultimately inconclusive evidence about Mars, and nobody was paying very much attention to the planet that is, depending on the time of year, anywhere from about 40 to about 260 million kilometers away. the planet you can see from your backyard on a clear night, shining in the twilight sky, beautiful and serene and terrible. And then Jane Greaves pointed a telescope at it. In September 2020, a team of astronomers pointed a telescope at Venus and found something that should not be there. A gas called phosphine. Phosphine. The chemical formula is pH3. One phosphorus atom bonded to 3 hydrogen atoms. It's a colourless gas. It smells apparently of garlic or rotting fish. It is deeply unpleasant and moderately toxic to human beings. Not a gas you want to be breathing. Not a gas that has any obvious reason to be in the atmosphere of Venus. The team was led by Jane Greaves, an astronomer at Cardiff University in Wales. Greaves had been interested in Venus as a potential habitat for some time, partly because of the cloud layer chemistry, and partly because she was, by professional inclination, the kind of scientist who looks at the things other scientists aren't looking at. She had been thinking about phosphine as a biosignature, a gas that could indicate the presence of life, for a while before she turned a telescope toward Venus specifically to look for it. The original observations were made with the James Clerk Maxwell Telescope, a large radio telescope located on the summit of Mauna Kea in Hawaii. The James Clerk Maxwell Telescope is about 15 meters in diameter, which is very large for a single-dish radio telescope, and it operates in the submillimeter and millimeter wavelength range, which is a part of the electromagnetic spectrum that is particularly useful for detecting molecules in planetary atmospheres. Different molecules have characteristic absorption and emission signatures at different wavelengths, like fingerprints, and the James Clerk Maxwell Telescope is very good at reading those fingerprints. Greaves and her team detected what appeared to be a phosphine signature in the Venusian atmosphere. They then sought follow-up observations from ALMA, the Atacama Large Millimeter Array, which is located in the Chilean desert at very high altitude, and is one of the most sensitive radio telescope arrays on Earth. ALMA is not a single telescope, but a collection of 66 individual radio antennas working together, spread across a high plateau in the Atacama Desert at about 5,000 meters altitude. The altitude matters because it puts the telescopes above most of the water vapor in Earth's atmosphere, which would otherwise absorb the signals they're trying to detect. ALMA confirmed the phosphine signal. The paper reporting the discovery was published in Nature Astronomy in September 2020, and it landed in the scientific community like a stone dropped in still water, not with a splash, with a slow spreading series of rings, a kind of quiet shock. Now, let's be careful here. Let's be precise about what was actually found, because the scientific story that followed the discovery is complicated and the details matter. The phosphine was detected spectroscopically. Spectroscopy is the technique of analyzing light, or in this case radio waves, to identify the chemical signatures of different molecules. Each molecule absorbs or emits radiation at specific wavelengths, and those wavelengths are like a molecular identity card. The phosphine molecule has a very specific spectroscopic fingerprint at a wavelength of about 1.123 millimeters. Greaves' team found absorption at that wavelength in the Venusian atmosphere. The concentration they measured was around 20 parts per billion. That's a small number. 20 molecules of phosphine for every billion molecules of other stuff in the Venusian atmosphere. On Earth, the amount of phosphine in the atmosphere is essentially zero, or near enough to zero to not show up in most measurements. So 20 parts per billion against that background is significant. But here's the thing, 20 parts per billion is also a small enough number that any measurement uncertainty or calibration error could theoretically explain it away. And this is exactly what the controversy that followed was about. Let's stay with what was actually found for a moment though, because even at the level of pure detection, the the phosphine signal was real enough to be published in Nature Astronomy, one of the most rigorous and well-regarded scientific journals in the world. The peer reviewers, who are expert scientists tasked with examining papers critically before publication, found the methodology sound. The signal was there. The question was what it meant. And to understand why it was surprising, you need to understand what phosphine is and where it comes from. On Earth, phosphine is produced in two main ways. First, by certain industrial processes. The semiconductor industry uses phosphine as a feedstock for depositing phosphorus onto silicon wafers. It's also used in some fumigation applications. These are human industrial processes, and they produce measurable amounts of phosphine near their sources, though the gas is reactive enough that it doesn't last long in the atmosphere and doesn't build up to globally significant concentrations. The second source is biological. Certain microbes, particularly anaerobic bacteria, the kind that thrive in environments without oxygen, produce phosphine as a byproduct of their metabolic processes. You find phosphine in swamps, in marshes, in the digestive systems of certain animals, in sewage, in places where organic material is decomposing in low oxygen conditions. The gas is produced by living things going about the business of being alive. Those are the two sources: industrial processes, living organisms. There are no industrial processes on Venus. There are no factories, no semiconductor foundries, no fumigation operations. Venus has never had a technological civilization producing phosphine as an industrial byproduct, which left the second option. Now, Greaves and her team were careful in the paper. They didn't say they had found life on Venus. They said they had found phosphine in the Venusian atmosphere at concentrations that could not be explained by any known non-biological chemical process, and that the most parsimonious explanation that remained after other explanations were excluded was biological production. They were careful, methodical, appropriately tentative. This is what good science looks like. Not "we found life," but "we found something we can't explain. Here are the things we ruled out. Here is what we're left with. Please help us understand this." And the scientific community responded, as it usually does to extraordinary claims, by trying very hard to find the ordinary explanation. The phosphine detection was about 20 parts per billion. Greaves's team had modelled all the non-biological phosphine sources they could think of. Volcanic eruptions, which produce various sulfur-containing gases and can produce small amounts of phosphine in some conditions. Lightning strikes, which can drive chemical reactions that produce exotic molecules. Photochemical reactions, driven by sunlight, that might produce phosphine from other atmospheric chemicals. Meteorite impacts, which bring phosphine-containing compounds from elsewhere in the solar system. They modelled all of these and found that the combined effect of all known non-biological phosphine sources in the Venusian atmosphere would produce concentrations of phosphine orders of magnitude below what they had measured. Not a little below. Orders of magnitude below. The gap between what the non-biological sources could produce and what was actually measured was enormous. If the measurement was correct, something extraordinary was making phosphine in the clouds of Venus. Right now, wherever you are, the air in your room contains traces of hundreds of different molecules. Most of them you've never thought about. Most of them have perfectly mundane explanations. Nitrogen from the atmosphere, oxygen, water vapor, carbon dioxide from your breath, small amounts of argon and methane and ozone and all the other trace gases that make up our air. None of these are mysterious. All of them have well understood sources. Now imagine someone from another planet using a telescope sensitive enough to detect the chemical composition of Earth's atmosphere from a distance, noticed an unusual concentration of a gas that, on their planet, was only produced by industrial processes and living organisms, and there were no industrial processes on Earth, only life. What conclusion would they draw? That is roughly the situation Greaves's team was in, looking at Venus. The phosphine concentration was, well, it was small, very small, parts per billion, which sounds like nothing. But in an atmosphere like Venus, even parts per billion of a biologically produced gas is extraordinary, because the Venusian atmosphere is chemically hostile to phosphine. The gas should be destroyed by the atmospheric chemistry, by the sulfuric acid, by the ultraviolet radiation, almost as fast as it forms. For phosphine to maintain a detectable concentration in that environment, something needs to be producing it continuously, producing it faster than the atmosphere destroys it. Something is acting as a phosphine source. The question is what? The paper came out and the scientific world started reading it. And then the controversy started. Not because the finding wasn't interesting, but because extraordinary findings in science always attract scrutiny. And scrutiny, in this case, found some things worth discussing. I think the paper came out in Nature Astronomy. Yes. September 2020. It was a Monday, I believe. Or maybe a Tuesday. I don't remember exactly. But I remember reading the coverage and feeling that particular kind of cognitive dissonance that comes when science produces something that your intuition about the universe says can't be right, but the data says might be. That feeling, that specific feeling of the world being stranger than you thought. Venus, right there in the evening sky, something you can see with your naked eye, might not be lifeless, might be in that cloud layer home to something microscopic, something utterly unlike us. But something, the planet you could probably see from your window if the sky is clear enough and you look at the right time of day. It sits there in the twilight, bright and still, and maybe not empty. Science does not sit still when something extraordinary lands in its lap. It shouldn't. That is actually one of the things that makes science trustworthy over time. Not that it gets things right immediately, but that it keeps pressing, keeps checking, keeps looking for the simpler explanation before accepting the complicated one. When the phosphine detection was published, the scientific community did exactly what it was supposed to do. It started pulling at the threads. The first major challenge came from a reanalysis of the ALMA data. ALMA, the Atacama Large Millimeter Array, had provided the higher resolution confirmation of the James Clerk Maxwell Telescope signal. But telescope data of this kind is complex. It requires calibration, it requires careful processing, and when a separate team of scientists went back and looked at the ALMA data very carefully, they found a problem. The data had been processed using a version of the ALMA calibration pipeline that contained a software error. Not a catastrophic error. Not the kind of error that invents a signal from nothing, but an error that affected the baseline of the data, the reference level against which the signal was measured. And when the data was reprocessed with a corrected version of the pipeline, the phosphine concentration dropped by quite a lot. The original measurement had been around 20 parts per billion. After the reanalysis, the ALMA-based estimate dropped to somewhere around 1 to 4 parts per billion, maybe lower. The exact number depended on the assumptions you made during reprocessing, and different groups of scientists making slightly different assumptions got slightly different answers. This is not unusual in science. The history of astronomy is full of cases where initial measurements, especially of faint signals in noisy data, turned out to be overestimates that were later revised downward. It's part of the process. You detect something, you report it carefully, you invite scrutiny, and the community does the work of checking. But here's the thing, even at 1 to 4 parts per billion, the phosphine problem didn't go away. Because even at those lower concentrations, the gap between what the known non-biological sources could produce and what was actually measured was still enormous. The non-biological models were predicting concentrations many times smaller than even the revised estimates. If anything, the gap had narrowed. But a significant gap remained. The question of the source was still open. Around the same time, other scientists began questioning whether what had been detected was phosphine at all. There is a molecule called sulfur dioxide, which is definitely in the Venusian atmosphere and is expected to be there given the planet's volcanic activity and sulfuric acid chemistry. And at certain wavelengths, sulfur dioxide has a spectroscopic signature that overlaps with the phosphine signature in ways that could, under some conditions, cause confusion. Could the signal be sulfur dioxide, misidentified as phosphine? The Greaves team had considered this. They had modelled the sulfur dioxide signature and argued that it couldn't account for the observed absorption. But other scientists weren't convinced, and a series of papers appeared in the months following the discovery, arguing that the signal was not phosphine at all, or at least that the phosphine interpretation was not established beyond reasonable doubt. This back and forth continued through late 2020 and into 2021. Papers appearing, counterpapers appearing, reanalyses, responses to reanalyses, the kind of extended scientific conversation that, from the outside, can look like a mess, but from the inside is exactly the system working as intended. And where did things settle? Honestly, they didn't settle cleanly. That's the honest answer. The scientific status of the phosphine detection, as of the most recent literature, is something like this. There is probably some phosphine in the Venusian atmosphere. The concentration is uncertain, but likely lower than the initial estimate. The non-biological explanations that have been proposed do not fully account for what was measured. The possibility of contamination or misidentification cannot be completely excluded, and the question remains genuinely open. Open. That word. It keeps coming back. The phosphine debate is a live scientific debate, not a resolved one, not a question with a consensus answer, except possibly the consensus that we need better data, more observations, ideally a mission to Venus that can do the measurements in situ, directly in the atmosphere, with instruments designed specifically for this purpose. A telescope looking at Venus from Earth is, in terms of chemical sensitivity, like trying to determine the ingredients in a meal by smelling the kitchen from a considerable distance. You can pick up hints, you can make educated guesses, but you cannot know with certainty until you open the pot. Let's acknowledge the alternative explanations more fully because they deserve respect. The scientists proposing them are not trying to kill a beautiful idea. They are doing what they should be doing. Volcanic activity on Venus is real and substantial. The surface of Venus shows signs of extensive volcanism, both ancient and possibly ongoing. Some recent analyses of radar data from the Magellan spacecraft, which orbited Venus in the early 1990s, suggest that certain volcanic features on the surface show changes consistent with active or very recent eruption. And volcanoes on Earth produce phosphine, at least in small quantities, in certain conditions where magma interacts with phosphorus-containing rocks. Could Venusian volcanism produce enough phosphine to account for the signal? Most calculations suggest no. The amounts would need to be so large and the volcanic activity so continuous and so specifically located in the cloud layers that it strains credulity. But strains credulity is not impossible, and Venus has surprised us before. Lightning is another candidate. Lightning discharges are energetic enough to drive unusual chemical reactions. On Earth, lightning produces small amounts of nitrogen oxides that would not otherwise form at those rates. Could Venusian lightning produce phosphine from the atmospheric chemistry in ways we haven't modelled correctly? The numbers don't work well here either. Estimates of the phosphine production from lightning in the Venusian atmosphere fall far short of what would be needed. and Venus's lightning itself is still somewhat debated in terms of frequency and intensity. There is a more intriguing non-biological possibility that some scientists have proposed, which has to do with the phosphorus chemistry of the Venusian atmosphere itself. The chemistry of phosphorus in highly acidic oxidizing environments is complex and not fully understood. There could be, the argument goes, chemical pathways that produce phosphine in the Venusian clouds that we haven't yet identified. Pathways that don't require life. Pathways that are simply the product of unusual chemistry in an unusual environment. This is genuinely possible. It's actually the most scientifically humble position to hold because it acknowledges that our understanding of Venusian atmospheric chemistry, which is quite detailed in some respects, may have significant gaps. The universe does not always conform to our models. Sometimes it does things we haven't thought of. But here's the problem with the unknown chemistry explanation. From a scientific standpoint, it's not wrong to propose it. But it's also not a satisfying answer because it's not a specific proposal. It's an appeal to ignorance. We don't know all the chemistry, so maybe there's some chemistry we don't know that explains this. That might be true, almost certainly is true in the sense that there is always chemistry we don't fully understand. But it doesn't predict anything. It doesn't give us a testable model. It doesn't explain the phosphine so much as it declines to explain it. The honest summary is this. No non-biological explanation proposed so far fully accounts for the phosphine signal, even at the revised lower concentrations. The biological explanation is not proven and may not be correct. We are in a state of genuine uncertainty, which is uncomfortable, but which is also exactly where interesting science lives. And in the middle of all this uncertainty, something quiet and easy to miss happened. A group of scientists went back and looked at data from a NASA probe that visited Venus decades earlier, the Pioneer Venus Large Probe, which descended through the Venusian atmosphere in 1978, 40 years earlier. And in the old data, analysed with new techniques and new understanding of what to look for, there appeared to be hints of phosphine. Hints, not proof, not a clear detection. Hints, at concentrations consistent with what the 2020 papers had reported. A whisper of something in data from 40 years ago that no one had recognised at the time because no one had been looking for it. The phosphine may have been there all along, waiting. In data that had been sitting in archives for 4 decades. The answer, if there is an answer, was there in the 1970s. We just weren't asking the right question. There is something in that, something about the nature of discovery, about how the universe contains its secrets, not in places we haven't looked, but sometimes in data we already have, sitting in storage somewhere, waiting for someone to think of the right question. And the right question in this case was asked in the clouds. There is a place in the sky above Venus, roughly 50 kilometers above the surface, where something remarkable happens to the conditions. Below that altitude, the atmosphere of Venus is a furnace. The temperature climbs steadily as you descend. The pressure mounts. The chemistry becomes increasingly hostile. By the time you reach the surface, you are in the environment we've already described. The melting lead environment, the 2 hours until the probe dies environment, but at 50 kilometers and continuing up to about 60 kilometers, the temperature drops to somewhere between about 30 degrees and 70 degrees Celsius. The pressure at 50 kilometers is roughly what you'd experience at Earth's surface, around 1 bar. The pressure at the top of the cloud layer, around 60 kilometers, is considerably lower, more like the pressure on a high mountain, 30 to 70 degrees Celsius. Surface pressure equivalent, those are not comfortable conditions by any stretch, but they are conditions in which liquid water, if water were present, could exist. They are conditions in which proteins don't automatically denature, in which cell membranes don't automatically dissolve, in which the basic machinery of biology, as we understand it, could theoretically function. This is the cloud layer, the habitable zone of Venus, if Venus has one. The clouds themselves are predominantly made of concentrated sulfuric acid, as we discussed. Sulfuric acid at concentrations of up to around 90%, that is extraordinarily acidic, extraordinarily corrosive, by most measures deeply hostile to life. And yet, the acid is not the only thing there. The clouds also contain water, not much water. The amount of water vapor in the Venusian clouds is very small compared to Earth's atmosphere. But water is there. And in the tiny droplets of acidic cloud liquid, there is water mixed with acid, not pure sulfuric acid. And here is where the story of extremophiles becomes relevant. Extremophiles are organisms that thrive in conditions that would kill most life on Earth. The word means, roughly, extreme lovers, which sounds almost whimsical for organisms that live in boiling acid or at absolute zero or under crushing pressure. But they are real. They are here. They have been here for a very long time. Let's talk about some of them. Because understanding what life can tolerate on Earth is the key to understanding why the Venusian clouds are not obviously impossible as a habitat. Acidophiles are organisms that prefer, or at least tolerate, highly acidic conditions. The drainage from certain mines, particularly mines where sulfide minerals are exposed to air and water, produces water that can reach a pH of 0 or even negative values. Negative pH. Acid beyond the range where most organisms could survive for more than seconds. And yet, in the acid mine drainage at places like the Rio Tinto in Spain, there are microbial communities that are not merely surviving, but actively thriving. They use the acidic environment as part of their metabolism. They are not tolerating the acid. They are living in it in the same easy way that a fish lives in water. The pH of the Venusian cloud droplets has been estimated at somewhere around -1. Negative pH, extremely acidic, more acidic than the most acidic environments on Earth where life has been found to survive, but not, it seems, beyond the outer edge of what is theoretically possible. The acidophiles at Rio Tinto are living in conditions that approach, though don't quite reach, the acidity of the Venusian cloud droplets. And they're fine. They're going about their business. Then there are thermophiles, organisms that love heat. Bacteria and archaea that live in hot springs, in hydrothermal vents, in environments where the temperature would cook most other organisms. The record holder as of recent years for heat tolerance is a microorganism called Methanopyrus candeleri, which has been found growing at temperatures above 120 degrees Celsius, above the boiling point of water. In pressurized environments where water remains liquid above its normal boiling point, some organisms are doing just fine. The cloud layer of Venus is warm, but it is not above the temperature range where extremophile life has been found on Earth, not even close to those upper extremes. There are organisms on Earth that can survive in concentrated acids and high temperatures simultaneously. Organisms that live in volcanic hot springs in places like Yellowstone, where the water is near boiling and has a pH close to 0. Organisms that are simultaneously acidophiles and thermophiles. Organisms that have evolved to handle conditions that read, on paper, like a list of everything life shouldn't be able to handle. And there are, perhaps most intriguingly for the Venus question, organisms that live in clouds, in Earth's atmosphere, floating. Atmospheric microbiology is a relatively young field, and its findings are remarkable. The troposphere, the lowest layer of Earth's atmosphere, contains a startling diversity of microorganisms at any given time. Bacteria, fungi, viruses, archaea. They are carried upward from the surface by wind currents and thermal convection, and they can survive at altitude for days or weeks before eventually being carried back down in rain or settling out under gravity. Some of these atmospheric microbes are not merely passive passengers. There is evidence that certain bacteria can influence cloud formation by providing the nuclei around which water droplets condense. Some researchers believe that life has been using Earth's atmosphere as a transport medium and, in some cases, as a habitat for hundreds of millions of years. The concept of an aerial biosphere, a community of microorganisms living in the atmosphere rather than on a surface, is real on Earth. It is small, dispersed, and dependent ultimately on the surface below as a source of nutrients. But it exists. On Venus, the question is whether an aerial biosphere could exist without that dependence on the surface. Whether organisms in the cloud layer could find everything they need in the cloud layer itself, never descending to a surface that would destroy them, never needing to. A permanently aerial existence. The clouds contain sulfur compounds, they contain traces of water, they receive abundant energy from sunlight. Could a microorganism, sufficiently strange, sufficiently adapted, find enough to eat and enough water to drink in those clouds? There is a researcher named Sara Seager, an astrophysicist at MIT, who has been one of the most serious and productive thinkers about the possibility of Venusian aerial life. Seager and her colleagues have worked through the chemistry of what life in the Venusian clouds might look like in considerable detail. She has proposed a life cycle for hypothetical Venusian microbes that involves them drying out into spore-like forms when they drift too low, becoming dormant as the temperature and pressure increase beyond survivable levels, then being carried back up into the cloud layer by convection currents, where they rehydrate and resume active life. This is speculation. Seager is the first to say so, but it is informed speculation, grounded in real atmospheric chemistry and real biology. It is the kind of speculation that is worth taking seriously because it makes predictions, because it identifies what to look for, and because it identifies what would rule it out. And there is something else Sara Seager has pointed out that is worth thinking about. Life on Earth uses liquid water as its solvent. Water is the medium in which all terrestrial biochemistry takes place. DNA, proteins, cell membranes, metabolic reactions, all of them require water to function. We tend to think of this as a fundamental requirement for life everywhere. But why should it be? Water is what life on Earth uses because water is what was available on Earth. Other liquids can also serve as solvents for chemistry. Concentrated sulfuric acid, as it happens, can dissolve many organic compounds and support complex chemistry. It is not obvious that the sulfuric acid in the Venusian clouds would be incompatible with all possible biochemistries. It might be incompatible with Earth biochemistry. But a life form that evolved in sulfuric acid, that used sulfuric acid the way we use water, would have an entirely different chemistry. A chemistry we have not imagined in full because we have never needed to. This is one of the more intellectually vertiginous ideas in astrobiology. The possibility that life elsewhere does not merely exist in hostile conditions, but has built an entirely different molecular architecture for doing what life does. That life might not look like life as we know it, might not use any of the same molecular components, might be so alien that a sample of it, placed in a laboratory, would not immediately be recognized as biological at all. Detecting such life would be extraordinarily difficult. Our instruments are designed to look for the chemistry we know: carbon-based molecules, DNA, proteins, the specific metabolic signatures of terrestrial biochemistry. A life form using a completely alien biochemistry might exist right next to our instruments and not register as alive. This is partly why the phosphine detection was so striking. Phosphine, at concentrations that cannot be explained by known non-biological chemistry, is a biosignature that doesn't depend on finding specific biological molecules. It's an anomaly, a chemical that doesn't belong there in the amounts measured. Something that says, in the language of planetary chemistry, something is happening here that I don't understand. Whether that something is life, or whether it is some exotic and as yet undescribed chemistry, is the question. And as you lie there, in whatever room you're in right now, consider this. The clouds of Venus are about 40 million kilometers away at the moment, more or less, depending on where the two planets are in their orbits. Light takes a little over 2 minutes to travel that far. A signal sent from Earth to Venus takes a little over 2 minutes to arrive. It is not far. In cosmic terms, it is essentially next door. And in those clouds, right now, at this moment, while you are here and warm and breathing, something may be drifting through the sulfuric acid, cycling through the 4-day circulation of the Venusian atmosphere, doing whatever it is that it does, completely unaware of us, completely undiscovered, possibly not even recognizable as life by any instrument we currently have, or possibly just chemistry, just the universe doing strange things with phosphorus and sulfur and heat and acid. We don't know, but we want to know. And that wanting, that reaching toward the strange quiet possibility, is one of the more interesting things about being human. In 1967, a paper was published in the journal Nature. The journal Nature, which is still publishing today and is still one of the most prestigious scientific journals in the world, had in 1967 a shorter format than it does now. Papers were brief, dense, packed with ideas in a compressed space. And in that brief, dense format, two scientists published a paper with a title that was straightforward to the point of almost hiding the audacity of what they were proposing. The paper was called Expedition to the Clouds of Venus. The two scientists were Harold Morowitz, a biophysicist from Yale, and Carl Sagan, who went on to write Cosmos, who went on to become perhaps the most recognizable science communicator of the 20th century, who wrote Contact and The Demon-Haunted World and Pale Blue Dot, who stood at the intersection of science and wonder and spent his professional life trying to help the rest of humanity see what he saw when he looked at the universe. In 1967, Carl Sagan was 33 years old, young, but not without credentials. He had already been working on questions related to the origin of life and the conditions for extraterrestrial life for years. He was, even then, one of the people who took the question of life elsewhere in the universe seriously at a time when it was considered by many of his colleagues to be a slightly embarrassing enthusiasm, not quite respectable, the province of science fiction rather than science. And Sagan and Morowitz, in 1967, looked at what was then known about Venus, which was far less than what we know now, and proposed that the cloud layer of Venus, at the altitudes where temperatures and pressures were reasonable, might support microbial life. They were careful. They were cautious. They acknowledged the speculative nature of their proposal, but they made the case, with scientific seriousness, that the conditions in the Venusian cloud layer did not preclude life, that there was a region of the Venusian atmosphere where liquid water could exist, where temperatures were moderate, where the available chemistry could support simple metabolisms, and that life, if it had ever existed on Venus at all, might have migrated to and persisted in that region. They were working with very limited data. The Venera program was only beginning. The composition of the Venusian clouds was not yet firmly established. They didn't know about the sulfuric acid, not with certainty. They were making educated guesses based on incomplete information, and they were right to raise the question. But it was largely dismissed, not loudly dismissed, not publicly demolished in a famous debate, just quietly set aside, filed away under the category of interesting speculation but not really serious. The scientific community of 1967 was focused on other things. The space race was at its height. The moon was the priority. Mars was the next serious candidate for life beyond Earth. Venus, as more was learned about it, increasingly seemed like the wrong place to look. Too hot, too acidic, too strange. The Sagan-Morawitz paper did not vanish entirely. It was cited occasionally by people who were serious about astrobiology, but it did not launch a research program. It did not inspire a mission. It did not change the conversation in any lasting way. And so it sat in the archives. A paper published by two serious scientists in a serious journal, making a careful case for a possibility that nobody pursued. For more than 50 years. There's something quietly melancholy about that if you sit with it. Sagan died in 1996. He never saw the phosphine detection. He never saw the renewal of interest in Venusian life that his own paper had anticipated by more than half a century. He never heard anyone say, in the context of serious science, that he might have been right. And he might have been right. Let's think about what Sagan was doing when he wrote that paper. He was doing what he always did, which was taking the available evidence seriously and following it where it led, even when it led somewhere uncomfortable. He had an extraordinary capacity for holding uncertainty without either dismissing it or inflating it. For saying clearly and calmly, here is what we know, here is what we don't know, here is what the combination of those two things suggests, and here is why we should take it seriously. That capacity is rarer than it should be in any field, including science. Most people, when they encounter something uncertain, want to resolve the uncertainty quickly. Either it's true or it isn't. Either there's life on Venus or there isn't. The middle ground, the genuine "we don't know," is uncomfortable. It requires you to carry the question without the relief of an answer. Sagan was comfortable in that middle ground. He spent much of his career there, and he was not alone. In the decades after the 1967 paper, a small number of scientists continued to think seriously about life in the Venusian clouds, even when it wasn't fashionable. Mark Bullock, who has done significant work on Venusian atmospheric chemistry. Dirk Schulze-Markuch, who has written extensively about the possibility of life in the outer solar system and on Venus specifically. A persistent undercurrent of serious scientific interest that never quite went away, even as Mars got all the headlines. There's a particular kind of intellectual loneliness in working on a question that the mainstream considers unimportant. You know the question is real. You know the data is interesting. You keep seeing hints and patterns that suggest something is worth investigating further. And the field moves on around you to the sexier questions, the better funded projects, the targets with more political support and more popular appeal. Those scientists who kept thinking about Venus during the long decades when nobody was paying attention did something important. They kept the question alive. They kept refining the models. They kept accumulating arguments, not proof, but arguments, for why the cloud layer of Venus deserved serious attention. And then, in 2020, a signal appeared in a telescope in Hawaii. And everyone turned around and looked at what those patient, unfashionable scientists had been pointing at all along. Sagan would have found this satisfying, I think, not in a triumphant way, in a quiet way. The kind of satisfaction that comes from knowing you asked the right question, even if you didn't live to hear whether the answer was yes or no. He always said that the cosmos was all there was, or is, or ever will be. He meant it as a statement about scale, about perspective, about the vast impersonal grandeur of the universe. But he also believed, quietly and persistently, that the cosmos had not produced life only once. That the universe was too large, too old, too full of the same basic chemistry for consciousness and metabolism to have arisen only here. Venus was, in that framework, simply the nearest laboratory. Right there, close enough to see, close enough in principle to visit. And if Sagan's clouds harbour what Sagan thought they might, then the person who is perhaps most responsible for keeping that possibility alive through the long years of disinterest will have been, in the end, not wrong. He was often not wrong. That's the thing about Sagan that irritated some of his colleagues and endeared him to everyone else. He was often not wrong. Life in acid. Let's talk about what life can actually do, not what we might imagine life could do in some abstract speculative future. What life has already done, here, on this planet, in this solar system. Because the story of extremophile life on Earth is, in its own way, just as strange as anything we might imagine finding in the clouds of Venus. Life appeared on Earth somewhere between 3.5 and 4 billion years ago, maybe earlier. Some estimates push the earliest evidence of life back to 4.1 billion years. The evidence is indirect at those timescales, chemical signatures in ancient rocks rather than fossil structures, but it's real enough to take seriously. And here is what happened in the 4 billion years that followed. Life, which began as simple single-celled organisms in what was probably a very different ocean chemistry from what we have today, proceeded to colonize every available environment on the planet. Not just the environments that seemed obviously suitable, all of them. The deep ocean, the seafloor, the sediments beneath the seafloor, the rocks beneath the sediments. Life is found kilometers below Earth's surface, in solid rock, in tiny pores and fractures, living on the chemical energy released by geological processes, in complete darkness, without photosynthesis, without sunlight, at temperatures that vary from near freezing to above boiling, at pressures that would crush most surface organisms. These subsurface communities are collectively called the deep biosphere, and estimates of how much life exists in this environment are extraordinary. The total mass of microbes living in the deep biosphere may be comparable to, or even exceed, the total mass of all surface life on Earth. The deep ocean itself, in particular the hydrothermal vents that were not discovered until 1977, supports ecosystems based entirely on chemosynthesis, using the chemical energy of hydrogen sulfide and other compounds coming out of the vents rather than sunlight. These ecosystems were a revelation when they were found. They demonstrated for the first time definitively that life did not require sunlight, that photosynthesis, which we tend to think of as the foundation of all food chains, was not universal even on Earth, that there was another way. In Antarctica, under the ice of Lake Vostok, which has been isolated from the surface for somewhere between 15 and 25 million years, there are signs of microbial life. Life that has been sealed in a cold, dark, nutrient-poor environment for longer than the genus Homo has existed and is still going, still doing whatever it does, quietly, under kilometers of ice, with no knowledge in any sense that the world above has changed beyond recognition since it was sealed in. In the Atacama Desert, which is the driest non-polar desert on Earth and one of the most Mars-like environments we have, microbes live inside rocks. Not on the surface of the rocks, inside them. They have found a way to use the tiny amount of moisture that condenses within the rock structure, to use the light that filters through the translucent minerals, to build a life in a space measured in micrometers, in conditions so dry that the desert itself is used as a proxy for testing instruments destined for Mars. And then there is the acid. The acidophiles we mentioned briefly before deserve more time. The Rio Tinto, the Red River in southern Spain, is one of the most extraordinary environments on Earth. It runs red because of the high concentration of iron minerals dissolved in its extremely acidic water. The pH of the Rio Tinto is typically between 0 and 2. pH 0, for reference, is the acidity of battery acid. And in this river, there are dozens of microbial species that are not just surviving, but thriving. They form complex communities. Some of them are photosynthetic, some are chemosynthetic, some feed on the others. They have built an ecosystem in a river of acid. The Rio Tinto has been running this way for millions of years. Some estimates put its acidic chemistry back several million years, deep into geological time. The microbes that live there have had millions of years to evolve in that environment. They are not generalists making do. They are specialists, finely tuned to the acid, possibly unable now to survive in normal pH water. And here is the detail that always stops me. The chemistry of the Rio Tinto is actually considered a good analogue for what the Venusian cloud chemistry might be like, in terms of the iron-sulfur mineral interactions and the acidic water. Scientists who study the Rio Tinto are not just studying an interesting Earth environment. They are, in part, thinking about Venus. The iron-sulfur chemistry, the extreme acidity, the way that microbes interact with those chemicals. All of it is informative about what might in principle happen in the Venusian clouds. But the Venusian clouds are not just acid. They are also, to a significant degree, dry. The water activity in the concentrated sulfuric acid droplets of Venus is very low. Water activity is a measure of how available the water is for chemical processes. In concentrated sulfuric acid, even if water molecules are present, they are so tightly bound to the acid molecules that they are largely unavailable for biological use. The water activity in the Venusian cloud droplets is thought to be around 0.004 compared to 1.0 for pure water. And here is where the challenge gets serious. No known life on Earth can survive at water activity that low. The record for low water activity tolerance on Earth is held by certain fungi and archaea that can survive at water activities of around 0.60 to 0.70. Some halophiles, organisms that love salt, can function down to water activity around 0.75 because the salt binding of water in their environment is similar in some ways to the acid binding in Venus. But 0.004 is far, far below even those records. This is a real problem for the Venusian aerial life hypothesis, not an insurmountable one necessarily. Life on Earth has never had to evolve for water activity that low because no environment on Earth has water activity that low. An organism that had billions of years to evolve for that condition might develop biochemistry we've never seen. Biochemistry that doesn't depend on freely available water in the same way terrestrial life does. Or, as Seeger has proposed, biochemistry based on a different solvent altogether. But we should not pretend the challenge is small. It is large. The conditions in the Venusian cloud layer, even in the most favourable part of the habitable zone, are at or beyond the edge of what we know life can handle. They are not obviously incompatible with life in the way the surface is, but they are not obviously compatible either. The honest answer is that we don't know what life can do that it hasn't yet done on Earth. We know what life has done in 4 billion years of evolution in the conditions that Earth has provided. We don't know what life would do given different conditions, different starting materials, different pressures and temperatures, and chemical environments. The space of possible biochemistries is almost certainly larger than the single example we have. There's another consideration that Seeger has brought up, which is the question of what life in the Venusian clouds would actually look like physically. On Earth, cells use lipid bilayers as their membranes. Lipids are fats, molecules with a water-loving head and a water-avoiding tail, which arrange themselves spontaneously into double-layered sheets in the presence of water. This self-assembly is one of the elegant features of terrestrial biochemistry, but lipid bilayers don't work in concentrated sulfuric acid. They dissolve. So a Venusian microbe, if it exists, would need a different kind of membrane. Seeger's group has proposed that molecules called azotosomes, made from nitrogen-containing compounds, could form stable membranes in a liquid methane environment like that of Titan. For Venus, similar thinking is required. What kind of molecule could form a stable boundary between the inside of a cell and the surrounding sulfuric acid? What kind of chemistry could protect an interior space from the surrounding environment while still allowing nutrients in and waste products out? Nobody knows. But the question itself is interesting. The answer, if it exists, would be written in a chemistry of life so different from ours that we might walk right past it. The possibility that life, if it exists in the Venusian clouds, might be so fundamentally alien that we would not recognize it is one of the stranger implications of this story. We might already have data that contains the answer, in the spectra from those telescopes, in the old Pioneer Venus data, and we might not be able to read it because the alphabet is one we have never learned. That is the kind of thought that sits with you in the dark, not uncomfortably, just quietly, with a sense of how much is unknown, how vast the space of possible things is compared to the space of known things. You are breathing air right now, air that has been breathed before by everything that ever lived on this planet, recycled through the biosphere over billions of years, passed through the lungs of dinosaurs and the spiracles of ancient insects, and the membranes of single-celled organisms in Precambrian seas. You are connected, by the air in this room, to the deep history of life on Earth. 4 billion years of life, all of which survived, all of which found a way. If there is life in the Venusian clouds, it found a way too. Different, stranger, written in chemistry we don't know, but the same in its essence, the same in its persistence, the same in its fundamental refusal to stop. Let's talk about what life can actually do, not what we might imagine life could do in some abstract speculative future. What life has already done, here, on this planet, in this solar system. Because the story of extremophile life on Earth is, in its own way, just as strange as anything we might imagine finding in the clouds of Venus. Life appeared on Earth somewhere between 3.5 and 4 billion years ago, maybe earlier. Some estimates push the earliest evidence of life back to 4.1 billion years. The evidence is indirect at those timescales, chemical signatures in ancient rocks rather than fossil structures, but it's real enough to take seriously. And here is what happened in the 4 billion years that followed. Life, which began as simple single-celled organisms in what was probably a very different ocean chemistry from what we have today, proceeded to colonize every available environment on the planet. Not just the environments that seemed obviously suitable, all of them. The deep ocean, the seafloor, the sediments beneath the seafloor, the rocks beneath the sediments. Life is found kilometers below Earth's surface, in solid rock, in tiny pores and fractures, living on the chemical energy released by geological processes, in complete darkness, without photosynthesis, without sunlight, at temperatures that vary from near freezing to above boiling, at pressures that would crush most surface organisms. These subsurface communities are collectively called the deep biosphere, and estimates of how much life exists in this environment are extraordinary. The total mass of microbes living in the deep biosphere may be comparable to or even exceed the total mass of all surface life on Earth. The deep ocean itself, in particular the hydrothermal vents that were not discovered until 1977, supports ecosystems based entirely on chemosynthesis, using the chemical energy of hydrogen sulfide and other compounds coming out of the vents rather than sunlight. These ecosystems were a revelation when they were found. They demonstrated for the first time definitively that life did not require sunlight, that photosynthesis, which we tend to think of as the foundation of all food chains, was not universal even on Earth. that there was another way. In Antarctica, under the ice of Lake Vostok, which has been isolated from the surface for somewhere between 15 and 25 million years, there are signs of microbial life. Life that has been sealed in a cold, dark, nutrient-poor environment for longer than the genus Homo has existed and is still going. Still doing whatever it does, quietly, under kilometers of ice, with no knowledge in any sense that the world above has changed beyond recognition since it was sealed in. In the Atacama Desert, which is the driest non-polar desert on Earth and one of the most Mars-like environments we have, microbes live inside rocks. Not on the surface of the rocks, inside them. They have found a way to use the tiny amount of moisture that condenses within the rock structure, to use the light that filters through the translucent minerals, to build a life in a space measured in micrometers, in conditions so dry that the desert itself is used as a proxy for testing instruments destined for Mars. And then there is the acid. The acidophiles we mentioned briefly before deserve more time. The Rio Tinto, the Red River in southern Spain, is one of the most extraordinary environments on Earth. It runs red because of the high concentration of iron minerals dissolved in its extremely acidic water. The pH of the Rio Tinto is typically between 0 and 2. pH 0, for reference, is the acidity of battery acid. And in this river, there are dozens of microbial species that are not just surviving, but thriving. They form complex communities. Some of them are photosynthetic, some are chemosynthetic, some feed on the others. They have built an ecosystem in a river of acid. The Rio Tinto has been running this way for millions of years. Some estimates put its acidic chemistry back several million years, deep into geological time. The microbes that live there have had millions of years to evolve in that environment. They are not generalists making do. They are specialists, finely tuned to the acid, possibly unable now to survive in normal pH water. And here is the detail that always stops me. The chemistry of the Rio Tinto is actually considered a good analogue for what the Venusian cloud chemistry might be like, in terms of the iron-sulfur mineral interactions and the acidic water. Scientists who study the Rio Tinto are not just studying an interesting Earth environment. They are, in part, thinking about Venus. The iron-sulfur chemistry, the extreme acidity, the way that microbes interact with those chemicals. All of it is informative about what might, in principle, happen in the Venusian clouds. But the Venusian clouds are not just acid. They are also, to a significant degree, dry. The water activity in the concentrated sulfuric acid droplets of Venus is very low. Water activity is a measure of how available the water is for chemical processes. In concentrated sulfuric acid, even if water molecules are present, they are so tightly bound to the acid molecules that they are largely unavailable for biological use. The water activity in the Venusian cloud droplets is thought to be around 0.004 compared to 1.0 for pure water. And here is where the challenge gets serious. No known life on Earth can survive at water activity that low. The record for low water activity tolerance on Earth is held by certain fungi and archaea that can survive at water activities of around 0.60 to 0.70. Some halophiles, organisms that love salt, can function down to water activity around 0.75 because the salt binding of water in their environment is similar in some ways to the acid binding in Venus. But 0.004 is far, far below even those records. This is a real problem for the Venusian aerial life hypothesis. Not an insurmountable one, necessarily. Life on Earth has never had to evolve for water activity that low, because no environment on Earth has water activity that low. An organism that had billions of years to evolve for that condition might develop biochemistry we've never seen. Biochemistry that doesn't depend on freely available water in the same way terrestrial life does. Or, as Seeger has proposed, biochemistry based on a different solvent altogether. But we should not pretend the challenge is small, it is large. The conditions in the Venusian cloud layer, even in the most favourable part of the habitable zone, are at or beyond the edge of what we know life can handle. They are not obviously incompatible with life in the way the surface is, but they are not obviously compatible either. The honest answer is that we don't know what life can do that it hasn't yet done on Earth. We know what life has done in 4 billion years of evolution, in the conditions that Earth has provided. We don't know what life would do given different conditions, different starting materials, different pressures and temperatures, and chemical environments. The space of possible biochemistries is almost certainly larger than the single example we have. There's another consideration that Seeger has brought up, which is the question of what life in the Venusian clouds would actually look like physically. On Earth, cells use lipid bilayers as their membranes. Lipids are fats, molecules with a water-loving head and a water-avoiding tail, which arrange themselves spontaneously into double-layered sheets in the presence of water. This self-assembly is one of the elegant features of terrestrial biochemistry. But lipid bilayers don't work in concentrated sulfuric acid. They dissolve. So a Venusian microbe, if it exists, would need a different kind of membrane. Seeger's group has proposed that molecules called azotosomes, made from nitrogen-containing compounds, could form stable membranes in a liquid methane environment like that of Titan. For Venus, similar thinking is required. What kind of molecule could form a stable boundary between the inside of a cell and the surrounding sulfuric acid? What kind of chemistry could protect an interior space from the surrounding environment while still allowing nutrients in and waste products out? Nobody knows, but the question itself is interesting. The answer, if it exists, would be written in a chemistry of life so different from ours that we might walk right past it. The possibility that life, if it exists in the Venusian clouds, might be so fundamentally alien that we would not recognize it, is one of the stranger implications of this story. We might already have data that contains the answer. In the spectra from those telescopes, in the old Pioneer Venus data, and we might not be able to read it because the alphabet is one we have never learned. That is the kind of thought that sits with you in the dark. Not uncomfortably, just quietly, with a sense of how much is unknown, how vast the space of possible things is compared to the space of known things. You are breathing air right now, air that has been breathed before by everything that ever lived on this planet, recycled through the biosphere over billions of years, passed through the lungs of dinosaurs and the spiracles of ancient insects, and the membranes of single-celled organisms in Precambrian seas. You are connected by the air in this room to the deep history of life on Earth. 4 billion years of life, all of which survived, all of which found a way. If there is life in the Venusian clouds, it found a way too. Different, stranger. Written in chemistry we don't know, but the same in its essence, the same in its persistence, the same in its fundamental refusal to stop. Let's be fair to the skeptics. Let's be genuinely fair to them, because the skeptics are not wrong to be skeptical, and the alternative explanations for the phosphine signal deserve a full hearing. The case for life in the Venusian clouds rests for now almost entirely on one piece of evidence: the phosphine detection. One signal from one type of measurement confirmed by 2 telescope systems, then partly revised in the reanalysis. It is not a large evidentiary base. Extraordinary claims require extraordinary evidence, as Sagan himself famously said, and one disputed atmospheric measurement, however intriguing, is not extraordinary evidence. So let's go through the alternatives more carefully. Volcanoes first. Venus is a geologically active planet. there is good reason to believe that volcanic activity on Venus is ongoing, or at least very recent. Some analyses of the Magellan radar data have identified features that look like fresh lava flows. The presence of sulfur dioxide in the atmosphere is consistent with volcanic outgassing, and volcanoes on Earth do produce phosphine in small amounts under specific conditions. The conditions under which terrestrial volcanoes produce phosphine typically involve high temperatures and the presence of phosphorus-bearing minerals reacting in reducing environments low in oxygen. Venus is certainly high temperature. It has phosphorus-bearing minerals. But the Venusian atmosphere is not particularly reducing. The presence of sulfur dioxide and other oxidizing compounds makes the Venusian atmosphere oxidizing rather than reducing, which is not the most favorable chemistry for phosphine production by volcanic processes. The calculations on volcanic phosphine production at Venus have been done by several groups, and the consensus is that volcanic activity would need to be roughly 100 to 200 times more intense than anything we've observed or inferred on Earth to produce the observed phosphine concentrations. And even then, the phosphine would need to be produced specifically at the right altitude, in the cloud layer, because phosphine is quickly destroyed by the atmospheric chemistry. Phosphine produced at the surface would be destroyed long before it reached the cloud layer where it was detected. Could there be volcanic activity specifically in the cloud layer? There is no known mechanism for this, though some scientists have proposed eruption plumes that could carry phosphine-bearing material to altitude. These are speculative mechanisms that would require quite specific and unusual geological processes. Lightning is often invoked as a source of exotic atmospheric chemistry, and rightly so. Lightning can produce everything from ozone to complex organic molecules to nitrogen oxides that wouldn't otherwise form in meaningful quantities. But the energy balance for phosphine production from lightning in the Venusian atmosphere has been calculated, and the numbers are not encouraging. The estimated phosphine production from lightning falls short by several orders of magnitude of what would be needed. There's also the question of whether the appropriate precursor molecules for lightning-generated phosphine are even present in the Venusian atmosphere in the right concentrations. The unknown chemistry explanation is the one that's hardest to argue against and hardest to argue for. It is unfalsifiable in its most general form, which makes it scientifically unsatisfying, but it is also almost certainly true that our models of Venusian atmospheric chemistry are incomplete. We have not been to Venus's clouds with sensitive chemical instruments. We have atmospheric data from the Pioneer Venus probes and from the Venera probes, and we have remote sensing from telescopes, but we do not have the comprehensive in situ chemical inventory that would let us say definitively what reactions are happening in the cloud layer. It is possible, genuinely possible, that there are phosphorus-bearing compounds in the Venusian atmosphere that we haven't identified, and that those compounds are undergoing reactions we haven't modelled, and that those reactions produce phosphine as a product. It is possible that the chemistry of highly concentrated sulfuric acid at the temperatures and pressures of the cloud layer includes pathways that are simply not well characterized. This is not a comfortable scientific position, but it is honest. The question is how to move forward, and that's where the scientific community found itself after the dust of the initial controversy settled. Not with a clean answer, not with a consensus, but with a recognition that the phosphine detection, however disputed in its details, had identified a genuine anomaly that needed explaining, and that the only way to explain it definitively was to go there. There was also a broader point made by some researchers that got less attention than it deserved. Even if the phosphine detection turned out to be wrong, even if it was eventually explained by sulfur dioxide contamination of the spectral data or by some exotic chemistry, the exercise of seriously engaging with the question of Venusian aerial life had revealed how little we actually know about the planet, how thin our data was, how much we had assumed without checking. We had, in a sense, neglected Venus. Mars had received enormous attention and enormous resources because it seemed like the more tractable target, the more likely place to find life, the more accessible world. And Mars is genuinely interesting. The evidence for ancient water, for ancient habitability, for possible subsurface environments where liquid water might persist today is compelling. Mars deserves its attention. But Venus had been neglected, not just as a target for life searches, but as a subject of scientific study. The last dedicated Venus mission by NASA was Magellan, which completed its radar mapping of the surface in 1994 and was deliberately deorbited in October of that year. That's more than 30 years ago. More than 30 years without a major American mission to the second planet. Europe sent an orbiter, Venus Express, which operated from 2006 to 2014. It produced valuable science about the Venusian atmosphere and confirmed, among other things, that the south pole of Venus has a fascinating double vortex structure. But Venus Express was not equipped to directly measure the chemical composition of the cloud layer in the detail needed to settle the phosphine question. Japan sent an orbiter, Akatsuki, which successfully entered Venus orbit in 2015 after a dramatic 5-year delay following a failed orbital insertion in 2010. Akatsuki has been studying the Venusian atmosphere, including the cloud dynamics, but again without the instruments needed for the specific chemical measurements that would address the phosphine question. And so, as of the present, we are still relying on telescope observations from Earth, imperfect and limited as they are, to try to understand what is happening in the clouds of a planet 40 million kilometers away. The phosphine controversy, in the end, may be most valuable not for what it revealed about the Venusian atmosphere, but for what it revealed about the state of planetary science, about the choices that had been made, about which questions were considered important and which were considered marginal, about the fact that we had, for 3 decades, been looking away from our nearest planetary neighbour. That is changing now. The phosphine detection and the controversy it ignited, and the broader conversation about Venusian aerial life that it reignited, Sagan's half-century-old question, suddenly alive again in the hallways of planetary science departments, contributed to a renewed interest in Venus that is now, finally, translating into missions. But those missions haven't arrived yet, and so the question sits open, still open. Like a door left slightly ajar in a dark room. You can see a thin line of light at the edge. You can't yet see what's on the other side. 3 missions are headed to Venus, not 1. 3. All announced within a relatively short window of time after decades of neglect. It feels from the outside like a field waking up, like a slow collective turning of attention towards something that had been sitting, patient and bright, in the evening sky, waiting to be taken seriously. Let's talk about them one by one. The first is Da Vinci. The name stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging. It's a NASA mission, and its approach to Venus is fundamentally different from anything that has been sent there before. Da Vinci is not an orbiter. It is not a lander in the traditional sense. It is a probe designed to fall through the Venusian atmosphere, slowly, on a parachute, and then in free descent, taking measurements the whole way down. The probe will enter the Venusian atmosphere and spend roughly an hour descending through it, from the cloud tops all the way to just above the surface. And during that hour, it will do something that no spacecraft has done since the Soviet Venera program ended in the 1980s. It will be there, inside the atmosphere, taking direct measurements, tasting the air, in a sense, rather than sniffing it from a distance. Da Vinci carries instruments designed to measure the chemical composition of the atmosphere in unprecedented detail. The noble gas measurements, which give the acronym part of its name, are important for understanding the history of Venus, how it formed and evolved, what it was like early in its history. But the chemistry measurements are important for the phosphine question, for the life question, because Da Vinci will pass through the cloud layer, through that 50 to 60 kilometer altitude band where the habitable zone sits, where the phosphine was detected, and it will measure what is actually there. If phosphine is present, Da Vinci should be able to detect it. If sulfur dioxide is being mistaken for phosphine in the telescope data, Da Vinci will measure the sulfur dioxide and set the record straight. If there is some exotic chemistry happening in the clouds that produces compounds we haven't anticipated, Da Vinci may find those compounds. Da Vinci will also carry a camera that will image the surface of Venus as it descends through the lower atmosphere in the last few minutes before impact. The surface imaging won't tell us about clouds or chemistry, but it will give us the best visual data about a specific region of the Venusian surface since Venera 13 and 14 in 1982. A geological snapshot of a world we have barely seen. The probe will not survive the surface. None of them ever do, but it doesn't need to. The data will be transmitted to the Da Vinci entry system carrier, which will fly past Venus without entering the atmosphere and then relayed back to Earth. The probe itself will join the long list of machines that the planet has quietly consumed. The second mission is Veritas. Venus emissivity, radio science, INSAR, topography and spectroscopy. Another NASA mission. Where Da Vinci descends through the atmosphere, Veritas stays above it in orbit, mapping the surface with radar and infrared instruments that can see through the clouds. Veritas will produce a global topographic map of Venus with resolution far beyond what Magellan achieved in the early 1990s. It will look for signs of active volcanism. It will look for evidence of water in the mineralogy of the surface rocks. It will try to understand the geological history of a planet that we currently understand, in detail, far less well than we understand the Moon. Veritas has had a complicated recent history in terms of funding and scheduling. NASA delayed the mission in 2022 due to budget pressures, which was a disappointment to the Venus science community after the excitement of the renewed interest following the phosphine detection. The mission is still planned, but the timeline has shifted. These things happen in planetary science. Missions are expensive and they compete for limited funding, and sometimes the competition goes against them in a given budget year. But Veritas is still on the books. It is still planned. It will fly. The third mission is ENVISION. This is a European Space Agency mission planned for launch in the early 2030s. ENVISION will also orbit Venus, and it will carry a sophisticated radar system and a suite of spectrometers designed to study both the surface and the atmosphere in detail. ENVISION and Veritas have been designed with some coordination to avoid redundancy and to ensure that the two missions together cover more scientific ground than either could alone. ENVISION's atmospheric instruments are particularly relevant to the phosphine question. The mission carries a radio occultation experiment and a suite of spectrometers that will be able to study the chemical composition of the atmosphere at different altitudes. Not with the directness of Da Vinci, which is physically in the atmosphere, but with a level of sensitivity and specificity that Earth-based telescope observations cannot match. Between Da Vinci, Veritas, and ENVISION, the next 15 to 20 years will see more data returned from Venus than in the entire preceding half-century. The planet that was the most neglected major destination in the inner solar system after the Magellan mission went silent in 1994 is about to receive sustained coordinated scientific attention for the first time. And at some point in that period, we will know. We will know whether the phosphine is real. We will know what is producing it. We will know whether the chemistry of the Venusian clouds is explained by geology and physics, or whether something else is going on. We will not necessarily know whether there is life. Even a definitive detection of phosphine in the cloud layer, confirmed by Da Vinci instruments inside the atmosphere, would not by itself prove life. It would strengthen the case considerably. It would eliminate the possibility of spectral confusion with sulfur dioxide. It would put pressure on the non-biological explanations to do better, but proof of life would require detecting something unambiguously biological, an organic molecule in a pattern that screams biology, a structure that looks like a cell, a metabolism that is working. Da Vinci is not designed to look for life directly. Its chemistry instruments will measure atmospheric composition, but they are not astrobiological instruments in the way, for instance, that the instruments on some Mars rovers are designed with life detection explicitly in mind. Getting a Venus mission designed specifically for life detection through the scientific peer review and funding processes is harder than it sounds, because the scientific community is appropriately cautious about committing major resources to a search whose target is still so speculative. But the conversation has changed. The phosphine detection, whatever its ultimate explanation turns out to be, opened a door that had been closed for decades. It made Venusian aerial life a topic that could be discussed in serious scientific papers without the author worrying too much about professional credibility. It gave permission, in a way, for the serious scientific community to engage with a question that had previously been just slightly outside the boundary of mainstream respectability. That permission matters. Ideas that scientists feel free to explore openly get explored. Ideas that seem professionally risky get left in drawers. Sagan's 1967 paper was partly left in a drawer for 50 years. The 2020 phosphine detection took it out of the drawer and put it on the table where everyone could see it. And now 3 spacecraft are being built or planned or funded to go and look. There is something satisfying about the pacing of this, the long wait, the decades of neglect, the lone voices in the wilderness of the planetary science community, and then the sudden attention. The way science sometimes moves in long, slow arcs and then curves sharply when the right observation comes along. The phosphine detection may not in the end be the discovery that confirmed life on Venus. It may be the observation that caused us to take seriously enough of a look that eventually the real discovery was made. That happens in science. The famous discovery is often not the one that mattered most. Often what mattered most was the question that got asked 10 or 20 or 50 years earlier, the paper that nobody cited, the observation that seemed ambiguous, the scientist who wouldn't stop looking. Somewhere in the archives of Venus science, in data collected by Soviet probes in the 1970s and 1980s, in measurements made by Pioneer Venus in 1978, in the spectra from telescopes that were pointed at Venus not to look for life, but to characterize its atmosphere, there may be evidence. Evidence that has been there for decades. Evidence that is waiting for someone to ask the right question. The cloud layer is patient. Whatever is in it, whether that is biology or strange chemistry or something we have not yet imagined, it has been there for a long time. It has survived the decades of our inattention. It will be there when Da Vinci finally descends through it. And if it's life, it will have been there, floating through the sulfuric acid on a 4-day circulation cycle around the planet, for longer than we can easily imagine, patient, drifting, unchanged. Let's say it's there. Let's follow that possibility out to where it leads, carefully, honestly, without exaggerating what it would mean or understating it. Let's say that Da Vinci descends through the Venusian clouds and the instruments confirm phosphine at concentrations that cannot be explained by any known chemistry. And let's say that a subsequent mission, one with instruments designed specifically for life detection, finds something in those clouds that is unambiguously biological: a microbial cell, an organic molecule in a configuration that only biology produces, a metabolic signal that only a living organism could generate. What would that mean? The first thing it would mean is that life arose independently twice in the same solar system, on Earth and on Venus, two separate origins of life, two separate occasions on which non-living chemistry crossed the threshold into something that reproduces, that evolves, that maintains itself against the disorder the universe is always trying to impose on it. Or it would mean that life arose once and spread from one planet to the other via panspermia, the idea that life can travel between planets, carried in rocks blasted into space by asteroid impacts, surviving the journey through interplanetary space, and then landing and surviving on the destination planet. Panspermia is a real and seriously discussed idea in astrobiology. We know that rocks from Mars land on Earth. We know that the conditions inside certain rocks, where organisms can shelter from radiation, can remain survivable during the transit. We know that some microbes can survive extraordinary conditions if they are in the right protective environment. But panspermia between Earth and Venus would be a longer journey, with a harder destination, and the survival probability is uncertain. It's possible. It's also possible that the two biospheres, if both exist, arose completely independently. Two origins of life in one solar system. That single fact, if it were established, would do more to change our understanding of life's frequency in the universe than almost anything else you could imagine discovering. Here is the logic. We currently have one data point, one planet with life, one example. And with one data point, you cannot do statistics. You cannot say whether life is common or rare. You cannot say whether the universe is full of biology or whether we are a singular accident. One data point is not a sample. It's an anecdote. If you have two data points, both in the same solar system, the picture changes completely. Two origins of life in the same solar system would suggest that the process of life's origin is not extraordinarily improbable. If life can start twice in one solar system, from similar raw materials, in similar conditions, then the probability of abiogenesis, of life starting from scratch, must be reasonably high whenever the conditions are right. And if the probability of abiogenesis is reasonably high, and the conditions for it are found across the universe in the billions of habitable worlds we now know exist, then the universe is probably full of life. Not necessarily full of intelligent life, complex life, life with technology and culture, and the desire to communicate across the stars. That's a different question. But full of microbial life, full of the basic, persistent, ancient kind of life that covered this planet for 3.5 billion years before anything with a backbone or a brain appeared. Full of the kind of life that doesn't care whether it's discovered, that doesn't send signals, that just floats in an acid cloud or lives in a rock fissure or photosynthesizes in a polar ocean, doing what it does, indifferent to its own significance. The universe in that picture would be saturated with biology. Every rocky planet with liquid water somewhere, every moon with a subsurface ocean, every cloud layer of every gas giant where the chemistry is right. All of it, probably, touched by life. All of it probably a version of what we have here. That is what two data points in one solar system would imply. Let's talk about the Drake equation because it's relevant here. Frank Drake was an astronomer who, in 1961, organized the first conference on the search for extraterrestrial intelligence. To focus the discussion, he wrote an equation on a blackboard. An equation that broke the question of how many communicating civilizations might exist in the galaxy into its component parts. The Drake equation is not a calculation exactly. It's more of a framework. a way of identifying what we need to know to answer the question. The equation multiplies together the rate of star formation in the galaxy, the fraction of stars with planets, the fraction of those planets that could support life, the fraction of those on which life actually arises, the fraction of those on which intelligent life arises, the fraction of those on which technology develops, and the average lifespan of a technological civilization. Most of these parameters are now much better constrained than they were in 1961. We know the rate of star formation pretty well. We know from the Kepler Space Telescope and other exoplanet surveys that the fraction of stars with planets is very high. Probably most stars have planets. We know that the fraction of planets in habitable zones, places where liquid water could exist, is significant. The galaxy is full of potentially habitable worlds. The terms we don't know well are the biological ones. What fraction of habitable worlds develop life? What fraction of those develop intelligence? These have historically been the unknowns that allowed pessimists to imagine a galaxy full of habitable worlds and utterly devoid of life, because if the probability of abiogenesis is small enough, even a galaxy with hundreds of billions of potentially habitable worlds might produce only one or a handful of inhabited ones. Life on Venus would constrain those biological terms dramatically. It would push the probability of abiogenesis from unknown, possibly very small, toward apparently not very small at all, given that it happened twice in the same solar system in a relatively short time. It wouldn't solve the Drake equation. There would still be deep uncertainty about the terms relating to intelligent life and technological civilization. A universe full of microbes drifting in acid clouds is not the same as a universe full of radio-transmitting civilizations. The Fermi paradox, the question of why, if intelligent life is common, we haven't heard from anyone, would remain unresolved. The Fermi paradox. Enrico Fermi, the physicist, is said to have asked, during a lunch conversation in 1950, something along the lines of, "Where is everybody?" If intelligent life is common in the universe, and if any sufficiently advanced civilization would eventually develop interstellar travel, or at least interstellar communication, then we should by now have seen or heard some sign of that. The universe is very old. There has been plenty of time, and yet the sky is silent. There are many proposed solutions to the Fermi paradox. Perhaps intelligent life is genuinely rare, even if microbial life is common. Perhaps civilizations tend to destroy themselves before they develop the capacity for interstellar communication. Perhaps the universe is full of signals that we're not looking for in the right way, at the right frequencies. Perhaps distance and the speed of light make communication so slow and expensive that even advanced civilizations don't bother. Perhaps we are in a quiet corner of a large universe, far from the main activity. Finding life on Venus would not resolve any of these possibilities, but it would make the first option, that life itself is rare, much harder to maintain. Because if life arose twice in one solar system, and if that solar system is not special in any obvious way, then it seems likely that life arises wherever conditions permit. And conditions permit across the observable universe in an enormous number of places. The silence of the sky would then require a different explanation. Not that life is absent, but that intelligence is rare, or that civilizations are short-lived, or that the distances are simply too vast. And there's something both comforting and unsettling in that picture. A universe full of life, most of it microscopic, most of it floating in clouds or living in rocks or cycling through the chemistry of alien oceans, unaware of anything beyond its immediate environment. Life as a property of matter, something the universe does wherever it gets the chance, like water finding its level, like crystals forming in a cooling solution. Not miraculous, not unique, just the universe, doing what it does, with the particular arrangement of atoms that we call biology. There is something enormously relieving in that picture. The loneliness of the pale blue dot, the image Carl Sagan described so unforgettably, that image of Earth as a mote of dust suspended in a sunbeam, visible through the viewport of the Voyager, one spacecraft at 4 billion miles away. The loneliness of that image, the smallness, the vulnerability. In the picture where life is everywhere, that loneliness dissolves. Not because we find neighbours with whom we can converse, but because the universe that seemed indifferent and cold and empty turns out to be, in its way, alive, not conscious, not communicating, not aware of us, but alive, doing what life does, persisting, adapting, covering whatever surfaces and filling whatever clouds and colonizing whatever darkness is available. A living universe. Not in the mystical sense, in the literal, chemical, biological sense. And if that's what Venus tells us when we finally go and look properly, then the pale blue dot will seem different. Not small and alone and fragile. Small, yes, and fragile, yes, but part of something. Part of a pattern that extends across a galaxy and probably a universe. Part of the thing that life does. Right now, the nearest other star to our Sun is Proxima Centauri, about 4 light-years away. There are planets orbiting Proxima Centauri, including one, Proxima Centauri b, that orbits in what we think is the habitable zone. We don't know if those planets have life. We don't know if they ever will. The journey there, at the fastest spacecraft speeds we currently have, would take tens of thousands of years. But Venus is right there, 40 million kilometers, a few months' journey with existing technology. If Venus has life, then the universe's answer to the question of whether we are alone is already visible in the evening sky, in the planet that ancient humans watched with reverence and wonder, in the brightest star in the twilight. The answer might already be there. We just haven't asked clearly enough yet to hear it. The planet Venus right now is somewhere in the sky. Whether it is visible from where you are tonight depends on the time of year and the time of night, on which side of the Terminator it happens to be, on whether the sky is clear, on whether you happen to be facing the right direction. But it is there. It is always there. It has been there for 4.5 billion years, going around the Sun on its slightly smaller, slightly faster orbit, taking about 225 Earth days to complete one trip. While you have been lying here tonight, while you have been listening to this and letting the ideas settle through you, Venus has moved, not dramatically, a small arc of its orbit, a fraction of a degree perhaps, but it has moved, and the clouds above its surface have moved too, circling the planet on that 4-day wind, carrying whatever they carry in their acid droplets, turning slowly in the light of the same sun that will rise tomorrow morning outside your window. The room you are in, right now, is at whatever temperature it is. Maybe 18 degrees, maybe 22, maybe a little warmer if it's summer, a little cooler if the heating is down for the night. Whatever it is comfortable enough. It is a temperature at which water is liquid, at which proteins function, at which the molecules of your body can do what they do. A temperature at which you are possible. On the surface of Venus, the temperature is around 465 degrees Celsius. It has been that way, more or less, for hundreds of millions of years. The surface is still, not silent perhaps. There may be volcanic activity, seismic activity, the deep groan of a geologically active planet. But no wind, not at the surface, because the thick lower atmosphere moves too slowly to feel like wind. Just heat and pressure, and the orange-yellow light filtering down through kilometers of cloud, and the flat angular rocks that Venera 13 photographed 40 years ago, unchanged. 50 kilometers above that surface, the clouds begin. And in the clouds, at the altitude where the temperature drops to something close to what you are feeling right now, something is happening. Something we have measured, however imperfectly, however ambiguously. A gas that doesn't belong there. A chemical signal in an environment that should have no source for it. Maybe it's chemistry. Maybe there is something in the phosphorus cycle of the Venusian atmosphere that we haven't figured out yet. Some reaction between the sulfur compounds and the minerals carried up from the surface in volcanic plumes. Some photochemical process we've been modeling incorrectly. Maybe the universe is just strange in a way that looks like life but isn't. Maybe. Or maybe in those clouds right now, something is alive. Something small. Smaller than anything you could see without the right instruments. Something that has no awareness of itself, no desire, no purpose in any human sense. Something that simply metabolizes, reproduces, drifts, metabolizes again. Something that doesn't know it is on Venus, doesn't know there is a Venus, doesn't know there is a universe, doesn't know in any sense that 4.5 billion years ago, a young planet next door developed its own version of the same chemical magic and has been ever since looking outward, trying to understand what is out there. It doesn't know we are here. It doesn't know tonight. But the thought that it might exist, floating right now in the acid clouds of the planet next door, is one of the stranger and quieter gifts that science has given us in recent memory. Not a certainty, not a proven fact, a possibility. A real, data-grounded, peer-reviewed, seriously entertained possibility. We are not alone. Maybe. Possibly. Perhaps. The maybe is honest. The honesty is important. Science advances through honest maybes, through careful uncertainties, through the refusal to claim more than the evidence supports. The phosphine detection was an honest maybe. The Greaves team did not say they had found life. They said they had found something that needed explaining. The community responded, appropriately, with skepticism and scrutiny and reanalysis. And at the end of all that, the question remained open. Open is not the same as unanswered. Open is not the same as empty. Open is a door that hasn't been walked through yet. Open is where the interesting things live before they become known things. And this particular open question will close, eventually. Da Vinci will descend. The spectrometers will run. The data will come back. More missions will follow. Better instruments. More targeted questions. At some point in the next several decades, we will know. Until then, the clouds of Venus hold what they hold. Patient, slow, ancient. Turning on their 4-day cycle around the planet, indifferent to our curiosity, indifferent to the 3 spacecraft being built to come and look at them. Tonight, you are here. Warm and still and breathing. You are in a room on a planet that got lucky. A planet that stayed at the right distance from its star. A planet that held on to its water. A planet that ran its carbon cycle correctly, that cycled its carbon dioxide between the atmosphere and the rocks and didn't let it pile up until the oceans boiled. A planet that, by some combination of geometry and geology and good fortune, stayed habitable while its twin went wrong. And in your lungs right now is air. Air with oxygen, which came from 4 billion years of photosynthesis. 4 billion years of life, doing what life does, modifying this planet's atmosphere so thoroughly that the air we breathe is itself biological. The oxygen in this room is a product of life. You are breathing the accumulated exhaust of 4 billion years of organisms that figured out how to split water molecules and release the oxygen as a byproduct. You are surrounded, literally surrounded, by the evidence of life. Not just your own life, the life of this planet, the long, slow, persistent life of Earth, which modified everything around it until the planet itself became unrecognizable from the dead rock it started as. Venus started in a similar place. And perhaps even after the surface went wrong, even after the greenhouse took hold and the oceans boiled and the rocks melted in the heat, something held on. Something moved upward. Something found the narrow ribbon of sky where the conditions were still almost reasonable and built a life there, improbable and strange and acid-soaked against all the odds of a world that had gone so catastrophically in the other direction. Perhaps that quiet, honest, scientifically grounded perhaps is not a small thing. It is one of the most interesting thoughts available to any human being lying in a dark room on a clear night, aware that the evening star in the sky above them might not be as dead as it looks. The universe is not empty. That is what tonight might be saying. Not proven, not confirmed, but hinted at in a spectroscopic signal in telescope data, in the models of a 1967 paper that nobody read carefully for 50 years, in the calculations of an MIT astrophysicist thinking about what kind of membrane a cell might use if sulfuric acid were the ocean it evolved in. The universe is hinting at fullness. You can let that settle now. Let it sit with everything else in the quiet of wherever you are. You don't need to resolve it. Nobody can resolve it yet. The most qualified scientists on Earth can't resolve it yet. All they can do is what you are doing, which is hold the question carefully, without crushing it, and wait for the answer to arrive. The answer will arrive. Da Vinci will descend through those clouds sometime in the next decade or so, and its instruments will run, and the data will come back, and people much smarter than any of us will spend years analysing it, and slowly, through the careful work of science, the question will either close or deepen. And somewhere in that process, we may find out something about the universe that changes how we understand our place in it. Not tonight. Tonight is just for wondering. Tonight is for lying in a room on a lucky planet, with air in your lungs that 4 billion years of life made breathable, and letting the thought of floating microbes in an acid cloud 40 million kilometers away be exactly as strange and exactly as wonderful as it is. You don't need to be awake for any of what comes next. The clouds of Venus will turn without you. The phosphine will do whatever it does, biological or chemical or something in between, undisturbed by your sleep. The 3 spacecraft being built in clean rooms on this planet will continue being built. The universe will continue its slow business, and you can rest now. You are exactly where you should be tonight, on the one planet in this solar system that kept its water, kept its oxygen, kept its moderate temperatures, kept its 1 bar of pressure, kept the conditions in which something like you could exist and breathe and wonder. You are on the lucky planet. And the lucky planet is dark now, and warm, and the room you are in is exactly the right temperature, and there is nothing you need to do except let sleep come. Let your breathing slow. Let the question of Venus drift, like a cloud particle in a 4-day wind, around the edges of your mind, not requiring an answer, not demanding resolution, just floating, just there, just possible. Good night.